Assalamu alaikum wa rahmatullahi wa barakatuhu. So we are continuing our continuous random variable chapter. So today's topic for the lecture is delta functions, mixed random variables. So we say that x is mixed random variable if range of x has at least one sample value with non-zero probability, like a discrete random variable, and also has sample values that cover an interval like a continuous random variable. The PDF of a mixed random variable contains finite non non-zero values and delta functions multiplied by probabilities. So here we can see once again that we say that x is a mixed random variable when we have the mix of both discrete and continuous random variables. So in discrete random variable, we know that the probability is defined on a per certain points, and in the continuous random variable, we know that the probability is defined over the interval. So combine, can make the PDF of this random variable. So we will have a special delta function we will see that is used to represent this mixed random variables, so that we can have a proper PDF. Although we have defined, so to represent these mixed random variables, we will introduce the unit impulse function delta of x. So that's the mathematical tool. That's actually a mathematical tool, a mathematical tool that unites the analysis of discrete and continuous random variable. The unit impulse, often called the often called the delta function. And that allows us to use the same formulas to describe calculations with both types of random variables. So the unit impulse function is defined as a unit impulse function. So to define this, let's define a function. Let f d epsilon of x is equal to 1 over epsilon for x is between epsilon by 2, negative epsilon by 2, and 0 otherwise. So then the unit impulse function, the unit impulse function is then delta of x equal to limit epsilon goes to 0 d epsilon x. So that can be seen in graph figure. So I will just copy it from the book. So this shows here d epsilon function. So this shows that for different values of epsilon, this is defined as from -1 over 2 to 1, and then if we have the epsilon 1, epsilon 1 by 2, 1 by 4, 1 by 8, and epsilon 1 by 16. So as we can see that as we are narrowing down or increasing this function, so or as we are reducing the epsilon value, so this function is reaching up to infinity. Means if we make a very big number, epsilon is equal to say 1 over some very big number, so that will be a very thin and very high amplitude delta function that we will get. So in mathematics, that it means that it has the area under it is 1, and it is defined only at point 0 in reality in mathematics. So and it has the amplitude of infinity, but obviously that is not properly numerical value that is for, but that is used for, but the properties that are given in this delta function are very important, and that's what we will be using them for. So the mathematical problem with the above definition is that d epsilon of x has no limit at x equals to 0 as shown in above figure. D epsilon of 0 just gets bigger and bigger as epsilon goes to 0. So, although the epsilon 0 blows up as epsilon goes to 0, the area under d epsilon of x is the integral defined as minus infinity to plus infinity d epsilon of x dx, which is equal to minus epsilon by 2 1 over epsilon dx equals to 1. So this area under d epsilon of x is always 1, no matter how small this epsilon value is. So we can say that minus infinity to infinity delta of x dx is 1. So area under this unit impulse function will always be 1. So here we will define a very important property of this delta function, and this is called the shifting property. In the shifting property, we know that for any continuous function g of x, so that integral g of x defined at the unit impulse defined at point x naught is equal to the function shifted to that point x naught. So this is a shifting property of we can say shifting property of delta function. So the shifting property of delta function. So next we define another function which is very close connection with this impulse function. We call that function as a unit step function. I hope these functions are not new for you people, because these are studied under the subject of signal system in detail. So here we will using it for only describing the mixed random variables. So the unit step function is u of x. It is 0 for x is less than 0 and 1 for x is greater than or equal to 0. Means it is like, so it is 0, so it is 0 before 0 and 1 here. So this is called the unit step function. So very important property and the link between delta function and the unit step function is that if we integrate uh, integrate the delta function, it will produce unit step function. Although we don't need to prove it, but we have to remember this thing, that if we integrate it, this delta function, so we will get this unit step function. So so the reverse is also true. So the reverse is also true, that if we if we differentiate the unit step function, we will get this delta function. Means if we differentiate u of x by dx, so we will get delta function here. So in both ways it is clearly defined. So let's start with how we are using these functions. So to find that, let's consider the CDF of a discrete random variable x. So we know that it is defined only at the certain points, and uh, except and where it has jumps at, it has the jumps of height given as px of xi. So using the definition of unit step function, we can write the CDF of x as so using the definition of the unit step function, we can write the CDF of x as fx of x is equal to summation xi that belongs to the range of x, px of xi, u of x minus xi. So we can obtain the PDF. We can obtain the PDF from here by integrating by differentiating it. So dfx of x by dx will give me the PDF, which is fx of x, which is equal to again summation xi that belongs to s of x, p x of xi, so that will remain the constant value, and if we differentiate this one, so that will give me the delta function u minus sorry x minus xi. So we can see that this is just a shifting property at all those points where these PMF is defined for discrete random variable. So we can define PDF for it. So अगर इसको हम गौर से दोबारा देखें तो हमारे पास CDF गिवन है. CDF में हमारे पास क्या है, जो हमारे पास PMF गिवन है और उसको हम डिफाइन कर रहे हैं कि किन किन पॉइंट्स के ऊपर हम उसको इन टर्म्स ऑफ यूनिट स्टेप फंक्शन दे रहे हैं. सो क्योंकि यूनिट स्टेप फंक्शंस को अगर हम उसके साथ मल्टीप्लाई कर देंगे तो हम देखते हैं कि जो जम्प्स हमारे पास CDF में आती हैं वो सेम चीज़ हमारे पास आ जाएगी. तो उन मुख्तलिफ जो यूनिट स्टेप्स हैं, यूनिट स्टेप्स क्योंकि जब प्रोबेबिलिटी के साथ मल्टीप्लाई हो जाएंगे तो उनका मैग्नीट्यूड वही आएगा जो इन प्रोबेबिलिटीज़ का इन पॉइंट्स के ऊपर डिफाइंड है XI के ऊपर. सो हमारे पास मुख्तलिफ किस्म की मुख्तलिफ एम्पलीट्यूड्स की हमारे पास आएंगी यूनिट स्टेप्स और उनको हम ऐड करते जाएंगे. सो अगर थोड़ा सा आप इसको विजुलाइज करेंगे तो हमें नज़र आता है कि हमारे पास अगेन CDF बन जाएगा. यूनिट स्टेप भी वही हमारे पास जंप शो करता है, जस्ट लाइक हमने देखा है कि हमारे पास अब ये मैग्नीट्यूड से 1 है. तो अगर हमारे पास मुख्तलिफ प्रॉबिलिटीज़ हैं तो उस हिसाब से इनका मैग्नीट्यूड चेंज होता जाएगा और उनको ऐड कर देंगे. सो ये जंप हमारे पास CDF में भी आती है जो हमारे पास डिस्क्रीट रैंडम वेरिएबल की है, तो यही हमारे पास होगी और उनको हम जमा कर देंगे तो हमारे पास fx आ जाएगा जो हमारे पास CDF है. अब अगर हम इसको डिफ्रेंशिएट करेंगे जी, तो हमारे पास जब डिफ्रेंशिएट करेंगे तो हमारे पास क्या आती है PDF. तो हमारे पास क्या आती है PDF, और PDF ही अगर हम देखें तो हमारे पास क्या है कि ये अब एज अ कांस्टेंट वैल्यू आ रही है. और जो यूनिट स्टेप है, यूनिट स्टेप को हमने देखा है कि अगर हम उसको डिफ्रेंशिएट करें तो हमारे पास डेल्टा फंक्शन बन जाता है. और हमने क्या कहा है कि डेल्टा फंक्शन अगर किसी फंक्शन के साथ मल्टीप्लाई हो रहा है और जिस पॉइंट पर वो डेल्टा फंक्शन डिफाइंड है तो उस वहाँ पर वो डेल्टा फंक्शन उस मैग्नीट्यूड का हमारे पास आ जाएगा जिसको हमने शिफ्टिंग प्रॉपर्टी कहा है। ये हमारे पास क्या था, जी ऑफ एक्स, और ये हमारे पास क्या है, डेल्टा एक्स माइनस एक्स आई, जिस पॉइंट के ऊपर हमारे पास ये फंक्शन डिफाइंड है। ओके, सो if we plot this thing, if we plot this function, that's quite easy. So this is say x here, so x1, x2, x3, x4 and so on. So we will get so, so we will get impulses, these called the impulses or the delta function with the, and we will write their probabilities given in the PMF at those points. Normally we keep their magnitude constant because we know that is a infinite in function, so that's a very huge, we cannot make that huge line here. So we normally use the same height for all these impulses or delta functions too, and we just write their probability which is px of xi at that point, which is defined in the PMF to represent this thing. Similarly, we can obtain the expected value for the discrete random variable. So that would be, expected value would be simple, ex, which is minus infinity to infinity x times xi, that belongs to range of x, px of xi delta x minus xi dx. So by writing the integral of sum as a sum of integrals and using the shifting property of the delta function, so we can see that we can write it as expected value of x. If we just take the summation out, and that would be minus infinity to infinity x px of xi into delta x minus xi dx. So that will simply give me the uh, these xi's using the shifting property. So that would be summation of xi that belongs to s of x xi times px xi. So let's have a look at the example so that we can have a bit clear picture of what we have studied so far. So it is example 4.19, and it says that suppose that we have given this PMF of y 1 by 3 for y is equal to 1, 2, 3 and 0 otherwise, and also the CDF is given, Fy of y is given as 0 for y is less than 1, 1 over 3 for y is between 2 and 1, and 2 by 3 for y between 3 and 2, 1 for y is greater than or equal to 3. So we have to represent this, we have to find its PDF, or in terms of impulse functions we can write. So we can write CDF in terms of unit step functions, that is 1 over 3 u of y minus 1 and plus 1 over 3 for u of y minus 2 plus 1 over 3 u of y minus 3. So how we can see that in figure? So let's have this. So if it is y, f y of y, so suppose it is 1 by 3, 2 by 3, and 1. So so it's defined say 1, 2, 3, 4, and so on. So it is 0 before here like this, and here up till 2, and here again jump and up till 3. So if we visualize that, we can see that we have three steps, three unit steps. One step is defined as u y minus 1. This is y minus 1, and another step is defined here with the magnitude of 1 by 3. So magnitude of 1 by 3 here. So it is defined as 1 by 3 here. That is another step. And again, we have the magnitude of 1 by 3 at y is equal to 3. So we have this unit step. So if we look at the definition of unit steps, so we have these three unit steps which are adding at different points so that it will give me the shape of this CDF. I hope you have understood how it's been related to these unit step functions. So if we now want to obtain the PDF of this function, so we need to differentiate it dfy of y by dy, so which will give me the fy of y. So if we differentiate this, it would be simply 1 over 3 delta y minus 1 plus 1 over 3 delta y minus 2 plus 1 over 3 delta y minus 3. So it simply means that the PDF will be in terms of impulse functions. So here we will have y, here we will be having the fy of y. So if we plot it, so at 1, 2, 3, we'll be having these impulses. So for them, for here, it has maybe the same magnitude, but even if their numbers are different, we have to plot them in the same length. So that's not a big deal. So we can also find out the expected value of this function. Expected value of y will be minus infinity to infinity y fy of y dy. So we can have this minus infinity to infinity y over 3 y over 3 delta y minus 1 dy plus minus infinity to plus infinity y over 3 delta y minus 2 plus minus infinity to infinity y over 3 delta y minus 3 dy. So by using this, we have seen this property. So that would be simply 1 by 3, 1 by 3 times multiplied by this by 1 by 3 xi. That's I will just rewrite this relation here. Expected value of x is equal to then summation of xi that belongs to range of s of x xi times px of xi. So xi is 1 into 1 by 3 here, and here it will be 2 into 1 by 3, and here it will be 3 into 1 by 3. So we will get this 1 by 3 plus 2 by 3 plus 1, so which comes out to be 2. So the expected value we will get is 2. So there is another important probabilities that we can find from here is if we f y of 2 minus. Just 2 minus simply means that just a little behind the 2. And if we look at this point here in CDF, so 2 minus means that just before 2, just before 2. So at 2 we can see that it is defined as 2 by 3, but just before 2 it is simply 1 by 3. So it is simply 1 by 3. Similarly, we can find Fy of 2 plus. So we have seen that it is just above the 2, just above the 2, very small above the 2. So we will having these values 2 by 3. So that CDF will give me the value of 2 by 2 by 3. So this is very simple, straightforward that we can get. So these actually last two probabilities, last two values, that gives us a very important theorem, and the theorem says that theorem 4.18, and it says that for a random variable x, we have the following equivalent statements. First one, it says that probability at x equal to x naught, which is give me some value q. Similarly, p x of x naught is again q. C says that fx of x naught plus minus fx of x naught minus will give me the same probability q, and fx of x naught, the PDF at x naught is q delta times at that point 0 or x naught. So these are all equivalent statements, so we must be very careful in defining or using these statements wherever we are implementing. So now next we have another definition, because now we are introduced with the unit impulse function and the unit step function, unit step function. So now we can define the terminology known as the mixed random variable. So we can define this terminology as mixed random variable. So the mixed random variable is defined as x is a mixed random variable. X is a mixed random variable if and only if and only if fx of x contains both impulses and non-zero finite values. So to understand this, let's solve a problem from the book. It is quiz 4.7, and it says that the CDF function of a random variable x is fx of x equal to 0 for x is less than -1, and fx of x equal to x plus 1 by 4 for between -1 to 1, and 1 for greater than 1. So first of all, we have to plot it to understand whether it is a mixed random variable or not. So It's simply to plot it. Here it would be x, and minus 1, 0, 1, 2, say 3, so, and say 1 by 4, 2 by 4, 3 by 4, 1, 1, 3 by 4, 2 by 4, 1 by 4. And this is fy of y-axis. So it is 0. It is 0 be, uh, before minus 1. So 0. Now it is a function x plus 1 by 4 between this. So at minus 1, if you just put minus 1, so it is minus 1, it is 0, and 0 it is 1 by 4. At 0 it is 1 by 4, and plus 1 it is 1 by plus 1 it is 1 by 2. So 1 by 2 is here, and at 1 now it is 1. So let's at 1 it is 1, and for greater than 1 it stays 1. Now here we can see that it's a continuous function because of x plus 1 by 4. But what happens here? Here we have the jump. Here we have this jump. Here we have this jump of 1 by 2. So it means that when we have this jump and the mix of continuous random variable, so we can say that this is a mixed random variable. So this is a mixed random variable. So let's solve these, answer these points which we have been asked to solve. So the part A says that we need to find the probability of x is less than or equal to 1, which is simply fx of 1. So fx of 1 is, just put it here, 1 plus so at here we can see at 1, if we see that at 1 it is 1, it is simply defined here from this function. So B part says that probability of x is less than 1. So it means that we know that less than 1 means simply 1 minus. So if we just just come before minus before 1, so we can see that we are at this point. We are at this point which is here, which is 1 by 2. So which is 1 by 2. So it is 1 by 2 from the graph or from the function we can see. And the third part says that what is the probability of x equals to 1. So if x equal to 1, we have done it before that we have to look it for x plus 1, 1 plus minus f of x 1 minus. So we can see that fx 1 plus it is 1 minus it is f of x 1 minus it is 1 by 2. So this will be at x equal to 1, it will be 1 by 2. Now next it says that the PDF of f of x, PDF PDF, we need to find fy of y. So we know that if we differentiate d fy of y dy, so we will get fy of y. So that comes out to be 1 by 4 for x is less than 1, greater than or equal to minus 1, and it is defined as delta x minus 1 by 2 for x equals to 1, because we have the jump here of magnitude 1 by 2. We have the jump of magnitude 1 by 2 times the delta x minus 1. So this is how we can define it otherwise. So if we plot it, that would be quite simple. If we just plot it, so here it is x, here it is fi of y. Sorry, it is yes, fi of I. Sorry, I just made it x. So between -1, 0, 1, its its value is it's 0 before here. Just change this color. So this is 0, and here it is 1 by 4, and it stays here, here, like this. But at 1, it has the unit impulse function, and its magnitude is 1 by 2. So this is how we can represent this mixed random variable. So I hope you have understood this mixed random variable. I urge you to practice some questions from the exercise and also follow these examples. The next topic is based on the MATLAB, as we have discussed in every chapter, that I will strongly suggest that you may follow this uh, article, which gives you some commands in the MATLAB to use these things, and you can visually see how you can use these functions in the MATLAB or some other software. So this book is using MATLAB, so you can use these some of the commands which are given here in this book. So that will give you a very clear picture and some future uh, implications of that, how you can use this subject for finding some complicated probabilities models to solve their to get the insight of those probability models. So I hope you understood all this lecture. So stay blessed. We will continue in the next lecture. Inshallah. Assalamu alaikum wa rahmatullahi wa barakatuh.